All right, 8.6 through 8.8 here. 8.6 is really just saying what we've already covered, that if you start out with H to H, that is purely covalent. H to C, you would start getting slightly polar. And the farther that you move until you get to HF is going to be extremely polar. Very, very similar to ionic at this point. And you just have that spectrum that you've got to always be looking at, that you have your nonpolar, your polar, and then your ionic. And all it is a matter of how much is that electronegativity, how much is the electrons shared between the atoms, and how much is it to just one side of the equation. Bonding then is just what are those electrons doing. The idea of bonding is one of our things. We enforce bonding on things. Just because we draw the picture of CH4 looking like this does not mean that that is how CH4 has to look. It's convenient for us to visualize that energy and that bonding looking like this. These H's can be in any way, fashion, or form, but this is probably the most stable configuration, and it is a good visualization tool for us. We also know that if I combust this and take it back to carbon and to hydrogens, I get out 1,644 kilojoules of energy per mole. And so it's really easy to say that for each CH bond, 413 kilojoules of energy exist. Now, could it be that this is 420 and this one is 417? Yeah, sure. That's remember, these are models, but we are going to be looking at it, and we are going to break things down and make it as simple for us as we possibly can. So when we talk about bond energies, we're going to look at them each separately, and we'll just make them as equal as we can. So if I have something, looking at enthalpy, something like CH4 plus 2Cl2 plus 2F2, and I put this into a combustor and I burn it, I'm going to end up with CF2Cl2 plus 2HF plus 2HCl. If I want to see if this is favorable, if it has a negative entropy, negative delta H, exothermic, what I can do is say, okay, here I have 4 CH bonds. And CH bonds have a energy of 413 kilojoules per mole. Here I have 2 Cl bonds. Okay, they have an energy of 478, that's a 4, sorry, kilojoules per mole. And I also have 2 F bonds, which have an energy of 154 kilojoules per mole. And sorry, I got to fix this. I jumped ahead of myself. I did my calculation too quick. This is 239 kilojoules per mole. Okay, so all my bonds that I have together on this side of my equation, if I add up all of their independent energies, I'm going to get, this one is 1652, so the 4 times the 413. This one is my 2 times my 239, so that's what I had written there, my 478. This is my 2 times my 154, so that is 308 kilojoules of energy. And if I add those all together, I get, in my bonds that I'm going to break here, 2,438 kilojoules of energy. Alright, so let's look at my other bonds that I'm going to form now. CF2Cl2 plus 2HF plus 2HCl. Well, here I'm going to have 2 CF bonds and 2 CCl bonds. Here I'm going to have 2 HF bonds, and here I'm going to have 2 HCl bonds. This guy is 485 kilojoules per mole, 339, and this would be something that you would look up on a table. 565. If you were in a lab, you would use your calorimeter that we've used in lab to test these and to see how much you're heating up your liquid. So I add these all together and I come up with 3,632. So now I just subtract the two. I go, my bond's broken, minus my bonds formed, and this works out because we want to know if the bonds formed is greater, then it's going to be exothermic, which should be negative. So this minus is what is going to do that for us, so that works out great for us. We said that my bonds broken were 2438. My bonds formed were 3632. So I get negative 1194 kilojoules. So this is an exothermic reaction, and you would expect this to go forward.